Well, a very good day to all of you and welcome to this webinar. Today, we have an opportunity to learn something about radars. Communications, navigation, surveillance, or CNS for short, are important enablers for air navigation service. Surveillance, in particular, can make a critical difference to our ANS provision. Radar has been a means for surveillance for quite some time now. In fact, radar is actually an acronym meaning radio detection and ranging. It was the United States Navy which first came up with this term in 1939. A number of nations developed the radar technology way back in the 1930s, just before World War II. Radar technology became a very critical asset for military use. Understandably, the military was a leader in a lot of radar applications. Well, I remember when I first started my career as an Air Force intercept controller a number of decades ago, we even had a height finder radar. The radar antenna would just scan up and down this way. It's quite unique. The controller would swivel the radar head to point at the target. And because in the older generation of military radars were not even three-dimensional, they were two-dimensional radars. So you actually needed a height finder radar. But of course, that has been changed. Most military radars are now three-dimensional today. And then I was operating on the E2C Hawkeye early warning radar plane. We had another unusual radar. It was a radar operating on the UHF band. And yet, if you know about typical radar frequency, that's quite unusual. This radar generates a pulse with a peak power of 1 megawatt. And that's also, if you know about the typical power generation for typical radar, that's not the case. It is one thing to have a radar fixed on the ground, but when you have a radar that's also flying, there's another level of complication in calculating the position of the targets. Radar has long been adopted by ANSPs to meet their surveillance needs. Today, the aviation world is using ADS-B. Do we still need radars? In ATC, there's a presumption of a cooperative environment in a changing world where unmanned aircraft or drones are common. As our operating airspace become more demanding, will there be more unknown flying objects interfering with ATC operations? For instance, there have been reports of airports being closed due to sustained drone interference. Should we change our expectations on ATC surveillance? And are there cost-effective radar technology transferable from military radar technology? To speak with us today on this topic, we have Lola Aguilera and Herman Rivera. First up is Lola. Lola holds a degree in telecommunications engineering and a master in business administration. She has 15 years experience in the ATM field within Indra, where she has been involved in the surveillance area, playing different roles as a system engineer, collaborating in building up systems requirements, and providing technical training courses. Since 2012, Lola is responsible for Europe and US market within the business development team of ATM Indra. Lola, you have the floor.
Thank you, Poh Theen, and hello everyone. Thank you, CANSO, for giving Indra the opportunity of being part of this webinar. So please, if you can go to next slide. Thank you. So in this first part, before Herman participation, I would like to give you a very brief overview of Indra for those who may not be familiar with it, and a brief explanation of the ATM capabilities focusing in the surveillance area, which is the topic of this webinar. So if you can go to the next slide. Okay, so this is Indra. We are a leading company in IT based in Madrid, in Spain. We are around 49,000 professionals all over the world. And well, our company is listed in the stock exchange, and the business figure of the company in terms of revenues for the last year is 3 million euros. And the company usually invests around 7-8% of the revenues in research and development. So this allows us to be at the forefront of the technology. Next slide. The company is composed of two different divisions. One of it is Minside, which is focused in digital and information technologies, and then Transport and Defense, which is subdivided into three different areas. Transport, which is dedicated to the technology applicable to the trains, buses, etc. Defense and Air Traffic Division, which is the division to where Herman and myself belong. So next slide. In ATM, Indra is a global player, leader in many regions of the world. We have over 5,000 facilities in over 160 countries, more than 100 years of experience in this market. By now, more than 80% of the world passengers are traveling using make of Indra ATM technology. Next slide. Well, we are proud to say that Indra has a wide portfolio that covers all the flight phases, so we are able to provide our customers with a solution that better fits their needs. Within our portfolio, and I guess that some of the participants in this webinar are already operating some of our system, we have like 6 different areas. Automation, in which we provide solutions for en route, approach, tower, and one of our latest solutions that we are providing are the remote towers, which are having, a high growth in the latest years. In the area of communications, through our brand Garex, we provide a system from the analog to the full IP system, which our Garex 300. In navigation, which probably is the range of solution in which the footprint is higher, we provide the Normax systems that includes ILS, DVR, and DME. We have a division of information with aeronautical information solutions that are led in Germany from our subsidiary Avitec. One of our latest solutions within the portfolio are the UTM platforms to safely integrate the flight of the drones within the air traffic systems. So finally, I left the surveillance because I am gonna go deeply on it. So if you can go to the next slide. Well, in surveillance, Indra has a footprint of over 580 systems in more than 90 countries. It is a huge experience that Indra offers to its clients from the initial phases of the project by helping our customers in the design of the surveillance network until the end of the life cycle of the system, supporting our customers in all stages. So within the portfolio, in the primary surveillance systems, we do provide a primary 2D, which is a system with a high accuracy and resolution and offering high reliability figures because it has a multi-crossing redundancy concept. And includes weather information, aircraft altitude estimation, and a detection range configurable between 60, 80, and 100 nautical miles. And the last but not least, it has clutter and wind farm mitigation techniques and immunity from LTE 4G interferences. Then in primary we have our L-band radar, which is a 3D radar, a phased array radar that provides inherent mitigation against wind farm and clutter. And if you compare the antenna size to L-bands, it's much smaller, so the infrastructure needed is much simpler. But I'm gonna leave it here because Herman will talk about it deeply. And in terms of cooperative systems, our secondary modest radar It's a system that we can provide in a standalone configuration or in a co-mounted operation with a primary radar 2D or 3D. And the main feature of our system or our last development is the smart ADS-B integration that obviously provides ADS-B information in the 256 nautical miles coverage, but give additional advantages like the reduction of the cone of silence, the improvement of the reflection process, passive acquisition, the reduction of the interrogation rate, and it has a digital receiver which enhance the capabilities of the systems. All the systems we are capable of providing to in transportable version based in a standard 20-feet containers that allow our customers to use the systems as temporary solution or as emergency backup for long periods. And finally, talking of non-rotating solutions, we do provide a single system that covers surface, wide area multilateration, and ADS-B. I mean, it's the same receiver station that covers the three functionalities. It is a system with a high accuracy that supports a high traffic density, and we provided the system in outdoor and indoor configuration for the station that makes our customer to save some money. Next slide, please. Well, this was about the traditional surveillance systems, and we have been thinking for many years in the future of the CNES, and we concluded the need of a borderless architecture for CNES with the drivers that are described in the slide. We need the need of rationalization the existing and global infrastructure, the need of having a cost-efficient infrastructure, and having in mind the hazards avoidance. So at the end, we bet for the space-based CNS understood as a service that we will provide to our customers. Next slide, please. So finally, last year, we founded Startical, which is a joint venture between ENAIRE and Indra that will provide ADS-B surveillance, real-time VHF voice, and air traffic data as a service. With a seamless transition. That means that there will be no need of changes or modification either in the aircrafts or in their control centers to use the service. So the idea is during the next year, we will launch the first constellation of satellites that will materialize the previous years of design. Next slide. So before giving the floor to Herman, I would like to briefly show to the audience our footprint in Asia and some very nice pictures of some of our installations in the region. So I hope you enjoy them. Please, next slide. Here in dark blue, we have the countries in which we have already system installed. My apologies if I forgot to include any. Well, we do have a network of offices with Indra personally in the region. The red dots, the pink dots that you can see there, that all these offices give supports to the ATM activities. So nowadays in the area we have around 140 surveillance systems, well, automation, BCS, and so. If you can go to the next slide. Here, I'm going to show you very quick some of our installation there. This is the Urumqi ACC in China. Next. The Incheon APP in Korea. Next. Murum MSSR in Mongolia. The technical room of a secondary radar in Phuket in Thailand. Next. That's a PSR-2D MSSR co-mounted in Vietnam. Next. PSR MSSR co-mounted in Korea. So here you can see the antenna. Next. This is another technical room for a secondary radar in China. Next. And this is a primary and secondary radar in Pudong, China. Next. So thank you very much. I will pass the floor to my colleague Poh Theen now. I will be back for the Q&A session.
Right, thank you, Lola. Next up is Herman, who will really bring us through all the technical details of radar technology. Herman is a telecommunications engineer and product manager specialized in radio frequency. He has been working on radar since 2007. He has been involved in business development activities, requirement analysis, and solution definition for different projects. He has been extensively involved in the primary radar technology roadmap, defining the development and strategy for primary radars for the future. Herman, yeah, next.
Thank you very much, Mr. Poh Theen, and thanks CANSO organization for this opportunity to participate in this webinar. So I want to talk to you a little bit about radar technology. So next slide, please. I want to of what is a radar. So Poh Theen already make an explanation. So a radar is a system able to detect an object, an aircraft in this case, emitting a radio wave that is transmitted and then waiting until it's reflected back to the radar and just measuring the time that it takes this travel. It is possible to measure the position or the range of the aircraft. There are several classifications that can be used to classify the technologies of the radar based on the aim of the radar or the different technologies. I will focus in a very basic and global one. Next slide, please. I will classify the radar between the non-cooperative radars, normally known as primary radars, and the cooperative radars, normally known in this world as secondary radars. So this classification is based in which equipment need to be on board the aircraft. For the non-cooperative radar, there is no need of any equipment in the aircraft. It's the radar its own, the one who detects the position of the aircraft, because the signal transmitted by the radar is reflected by the aircraft itself and coming back to the radar. Next slide, please. But when we talk about the cooperative radar, then it is necessary to have equipment on board in the aircraft. This is normally the transponder. So the radar, the secondary radar, sends an interrogation to the transponder in the aircraft, who answer back to the radar, and in this communication channel, it's possible to determine the position of the aircraft and also to have other information like the identification, altitude, and other important information for the operator. Next slide, please. So when talking about the cooperative surveillance, then we can have two classifications, two different systems. The independent surveillance, like the SSR, multilateral or WAM, where is the system needs to interrogate or to process the signal to locate the target. So the system is actively locating the target. When we are talking about the dependent surveillance, like ADS-B, is the equipment on board itself who sends the information to the system. So the GPS on board is getting the position of the aircraft, the latitude and the longitude, and send it to the radar. Next slide, please. So once we have done this classification about the system related to which equipment need to be on board the aircraft, we can also talk about the differences that we have in the military use of the systems and the civil use of the system. So they are quite different worlds with different requirements and different needs. In the military purpose, the primary radar is the main element. Normally, it's the one that is working always to detect an aircraft. Altitude reported by this primary radar is very important. It's used to locate the enemy, let's say. Data quality is not so relevant. It's important, but it's not so relevant. The most important is the disponibility of the system, to have the system available always to be able to detect the targets. And in this military world, the secondary radar, called IFF, Identifier Friend or Foe, is used after the primary mainly to identify if it's a friend or a foe and to accurately locate the target once it has been detected by the PSR. In the civil world, that sense is completely different. The secondary radar is the main element. Information like the aircraft ID, the barometric altitude reported by the transponder, and other information obtained from the secondary are very important for the controller. Data quality is the most important for air traffic control in the civil world. It's better not to have data that have incorrect data that can cause a problem to the operator. And the primary radar is used to reinforce the information obtained by the secondary radar, and of course as a backup and safety layer for the cooperative surveillance. This is very important also for such aircrafts or elements that are not having a transponder, like small aircrafts or drones, etc. Next slide, please. So Indra has a wide experience in both worlds, in the military and in the civil world. The Lance family in the military department of Indra comes from the early 80s, with radar primaries used vessels are for the early warning alert defense systems. And then we think, why not having the best things of both worlds, merging the technologies, including all the civil requirements, and getting just the best things and what is really needed of the military world into a system to be used in the civil world. And the result is obtaining the best radar option, that is the Indra PSR 3D ATM civil radar. Next slide, please. So talking about primary radars, we can differentiate two technologies, 2D radar and 3D radar. So in traditional 2D radars, the main difference between both systems is the antenna diagram and how it deals with the information. In traditional 2D radars, the antenna diagram is based in normally two wide beams in elevation. Normally they are called fan beams, where the signal coming from the clutter and for the aircraft is always mixed, and we need several techniques to differentiate what is the real target and the clutter. The clutter is everything that appears in the controller screen that is not a real aircraft, and we don't really want to detect such kind of things. In the 3D radar, as you see in the picture on the right or in the video, the technology of the antenna is completely different. It's based on different narrow pencil beams in elevation that are electronically scanning in vertical the elevation. So the advantage of this technology is that the aircraft and the clutter or the mountain, the building, whatever, is not detected together. So while we detect these clutter things, these mountains in the lower beams, we are able to detect the aircraft in a higher beam, which is nearly in clear environment without the affection of the reflection from mountains, buildings, or other objects. So this is a great advantage of the use of the 3D technology to improve the performance of the system. Next slide, please. So the Indra vision for the surveillance is completely aligned with the latest recommendations about from ICAO or Eurocontrol, based on which are the performance-based surveillance. I mean, we have to think about the surveillance service. We have to think in the performance we obtain with these services, and we have focused in two main KPIs, which are the safety and efficiency of the system. For the system, the safety, our recommendation is to use non-cooperative surveillance system. This is really important for TMA, where it's important to have information from those elements which are not equipped with a transponder, like drones or small aircraft. Also, in the same station, the recommendation is to include a double layer of cooperative surveillance. This is achieved with our secondary system that includes MODES and ADS-B all together. So we have the three layers all together in the same station: non-cooperative, cooperative independent, and cooperative dependent surveillance. And another important factor is the performance monitoring. So knowing in every moment which is the healthy of the systems installed, will help to the maintainability of the systems and to reduce costs of non-working systems in the surveillance network. And related to the efficiency, our idea is to minimize the needed infrastructure for the surveillance systems, new maintenance policies, for instance, the capability of do remote maintenance tasks that do not need the visit of the radar site, which are normally unattended and in remote positions. And also we can think, why not, in the surveillance system like as a service. This is in line with the Startical program presented by my colleague Lola before. Next slide, please. So this is, again, a summary of the portfolio of the Indra subsystems, which are covering all the classifications mentioned before. Next slide, please. So now let's talk a little bit more about the PSR 3D radar. Next slide. So traditionally, we can think in three different applications for surveillance: TMA application, approach application, and a route application. Normally, traditionally, for TMA and approach applications, S-band systems were used to reduce the infrastructure cost, and L-band systems were used in route applications. Our proposal with our PSR 3D system is that this system is able to be configured and to work in all three configurations. That will reduce the different hardware and the different systems that are needed in the network, in the surveillance network. Next slide, please. So which are the expectations for a primary radar or for a non-cooperative surveillance system? A good detection of probability, a good accuracy for the detection. Is important to have a precise position of the target, low false alarm rate that are not disturbing the controller from its operations, and to have a weather information picture with a high refresh rate. And which are the typical problems that we will find in the non-cooperative surveillance systems? The difficult adaptation to hard environment site. If we are in an environment with a lot of mountains, buildings, and wind farms, etc., it's difficult to achieve this good relationship between the probability of detection and low false alarm rate. Also, the installation infrastructure necessary, mainly when we were talking about traditional L-band 2D systems, and the system maintainability and availability. Next slide, please. So how can we focus in those elements with the 3D radar? So thanks to this vertical exploration of the coverage, the system is able to detect, to improve the detectability of the targets in hard clutter environments. Also, is improving the detection accuracy of the targets compared with a 2D radar, because thanks to the antenna, the technology using the antenna is able to use monopulse techniques. And also with a 3D radar, can be achieved also with a 2D radar, but with a 3D radar, we have an accurate non-cooperative target altitude report, having some more information that can help the controller during its operation. About the false target rate reduction, the system incorporates advanced tracking algorithms that are using this extra information obtained from the altitude of the aircraft. And also, thanks to the pencil beam exploration, the system has an inherent clutter mitigation capability, because we can treat different the lower beams which are detecting the clutter and the higher beams which are detecting the aircraft. There are also special techniques used both in 2D and 3D radars to achieve an extra clutter reduction by the combination of the different beams and creating a synthetic null in some elevation to reduce the signal that is coming from the mountain or the clutter itself. This, thanks to the antenna diagram used in the 3D radar, these techniques can be enhanced and we can achieve a better clutter rejection that if we compare with a 2D radar. Next slide, please. Also, when we are talking about the weather, the system incorporates a calibrated weather channel integrated with no additional extra packets in the system, which is configurable. It is reporting a picture, for instance, every 6 scans. This refresh rate is much faster than if we compare with a traditional specific weather radar, which is reporting a much more accurate weather picture, but with a refresh rate of the order of minutes instead of seconds, like the 3D radar. And also an additional feature is the capability of the estimation of the weather altitude that can help the controller in the decision of changing the route of the altitude of an aircraft, reducing operational cost in the air traffic control. Next slide, please. About the infrastructure, the smart antenna size used in the PSR allows to install the L-band system in the same way like an S-band system to be used in TMA and approach application. Next click, please. So if we see the typical L-band reflector antenna and we focus in the LBA antenna from the secondary, which is the one in the top, the size of this antenna is much more smaller than the parabolic reflector. Next slide. Sorry, I think. And if we compare it with the antenna of the 3D radar, which is the one in the bottom here, the biggest one is the one of the secondary. So that reflects that the infrastructure for the tower needed is not as big as for a traditional L-band radar with a parabolic reflector. Next scan. And well, the 3D radar allows a big flexibility in the adaptation to the environment, thanks to the electronic capabilities for tilting, sectorization, and adaptation of the range in the different sectors and areas that need to be covered. Next slide. And then we said that the primary radars are very important for safety reasons to detect elements with no transponder. And one of those elements are the drone detection. So this is not a specific drone detection radar, it's a surveillance radar, but thanks to the pencil beams and the scanning in elevation, the drone detection capabilities are improved respect to a traditional 2D radar. Next slide, please. So here I want to show you a small video about the test that we have performed with the drone detection. The drone was this matrix that you can see the picture on the left. It's a medium-sized drone, and then we can play the video and see how the system behaves with the drone. So what we would see in this video is a drone being detected by the radar. If you see this plot that is remarked in the screen, is the drone that is being detected. Okay, we see now one is tracked. The data is a very slow target, about 45 kilometers with this course, and also a very small one with a very small radar cross section, and also the altitude is reported by the 3D radar. So we can see how the radar is tracking the drone, reporting information about its speed, its altitude, and its radar cross section. And we will see now how the drone will do a hovering maneuver and a 180 turn back, and how the radar will be able to continue tracking the drone. So now in the next scan, we will see. Okay, so then the target is missed because it was making a hovering maneuver, but then the radar is able to detect it again and come back to track the drone and to continue giving information about the speed, the course, and the altitude, keeping the same track information. Okay, so that's the video for the example of how the radar was able to track a drone. So next slide, please. Well, just comment that we have also these systems with a deployable solution that reduce the need of infrastructure that can be deployed in a very fast, in few hours, to give a complete service for air traffic control. Next slide, please. And again, about the remote management and monitoring system, we think that is a key performance to reduce costs and to improve the maintainability of the system. Next slide. So we have put a lot of effort in developing a new CMS, including supervision, control, and maintenance, basic functionalities developed using the latest technology with a web-based interface. Next slide. And that can be used not only for one system, but to monitor a complete country, a complete region, and not only for surveillance, but also integrating navigation or other systems in the same monitoring network. Next slide. And we have focused also in advanced functionalities like remote maintenance, obtaining all possible data from the system to do kind of preventive maintenance using big data functionalities. And our main objective is to achieve a predictive maintenance functionality in a level 4 maintainability system. Next slide, please. So this is all from my part. I don't know if we are on time also to see a video summary for all the previous presentation and slides.
Right. Thank you very much, Herman. Well, some questions have come in, and among the questions, there seems to be a fair bit of interest on drone detection. In particular, what's the detection capability of this such a 3D radar, L-band radar, to detect drone, and what kind of sizes? I know you have you showed the video just now and you explained, uh, uh, could you like elaborate more on exactly what drone sizes, what range, because you did
Yeah,
mention radar cross section, but radar cross section depends on the material, the design of the drones.
yeah, for sure. So if we focus directly in the size of the drone to be detected, and we think about the power of the radar, we can. There is it was the graphic in some of the slides I saw before. We can calculate theoretically which is the coverage, and for instance, in the previous slide we saw that there was theoretical capability of detecting drones of around 0.01 square meters, which is a quite small drone, in let's say the first 40 to 50 nautical miles of the coverage. But the real problem for drone detection is not really the power of the size itself of the drone, is that the drone, when it's mixed with the clutter, the radar to detect the drone needs to have a good signal to clutter relationship. That figure is very difficult to achieve in a 2D radar, where okay, theoretically you could be able to detect the drone because of the power, but if you are mixing that signal with the clutter, then you will have a very bad signal to clutter and will not be able to detect the drone. That is quite different in a 3D radar because you can use different pencil beams in elevation to detect the drone over the clutter in a different environment. That helps a lot to the detection of drones in this kind of 3D systems. Also, the electronic configuration of the tilt allows to select a sectorized tilt, pointing the antenna diagram in the right elevation to detect drones over the terrain or over the clutter. So related to capabilities, we can say that this 0.01 for 50 nautical miles in a clear environment, but the big advantage of this system is the detection of drones in clutter environment. So this is the advantage if we compare with a 2D radar. I don't
Right.
know if
Thank
this
you.
helps to answer the question.
Thank you. There's another question here. What is the capability of this 3D primary surveillance radar to provide surveillance of HAPS, which flies slowly at 16 knots and then establish service delivery tracks at flight level 600 and above? HAPS, I don't know what it stands for, but I think it's something about high altitude.
High altitude. Okay. Yeah. Okay. With the 3D radar, the antenna coverage, the antenna diagram is configurable. So we can select different pencil beams to focus the energy in the altitude that we want to cover. So this is quite different from a 2D radar, which is a fixed antenna diagram based on a parabolic reflector. So if we want to detect targets flying at a high altitude, then we can configure and set up higher beams pointing to higher elevation to be able to detect such targets flying in high altitude. We have experience of detecting targets flying at 50,000 feet or 55,000 feet or even higher, even with no transponder, of course, in military flights, doing overflights in some area. So this 3D system allows huge capabilities for configuring the system to the aim that want to be used. And that also can be done in a sector way. So if we know that these kind of flights are only in one sector of the coverage, we can make a sectorization mode for the needs in that area while keeping the rest of coverage of surveillance in the other area.
Does it take long to reconfigure, to set this configuration, for instance, the particular sector that you want more energy or attention or surveillance, you know, or higher altitude, can it be done by the controller, or must it be done by an engineer offline?
Normally, what we do is to leave Indra engineering, leave in the system a set of different operational modes according to the necessities that the customer translate to us during the optimization or during the installation. This set of operational modes are stored in the system, and from the CMS with a graphical interface, it's possible to just in a few minutes say, from this azimuth to this azimuth, I want to use this kind of antenna diagram of exploration mode. So for the civil world in this system, the only thing that we need to keep constant is the rotation rate. So the update of the information will be constant, but the energy, how is focused the energy, or the antenna beams, the diagram that we are using, can be sectorized and selected by the operator in few minutes from the CMS, from a prefix setup of different exploration modes.
Right. Okay. Well, Herman, I have another question for you. Well, you know, radar engineering is about trade-off, right? So is it better to have like a suite of multiple radars, you know, each with a specialized function, you know, one for ATC surveillance, another to you know, detect drones, and perhaps another one for weather radar, all separate, and then integrate the information? Or is it better to have all these functions all in one radar?
Just depend on the of how exigent are you with the data that you want to achieve, but in a cost-efficient way, we think that it's better to have a radar that can have multiple capabilities and that can be configured differently in different sectors, also according to the needs that you have. That having completely different systems that are the cost, of course, increase having different systems, and also the maintainability cost, the operational costs, and so on is increasing. So we think that depending on how exigent is the needs for such in a particular place, we think it's better to have a radar that can cover multiple areas and can give multiple services.
Right. Thank you. Yeah. Yeah. Well, one more question really. Well, it's a follow-on question to that. You know, what would you say, or could you give us a sense of the difference in cost between having you know, that a 3D radar that can do, you know, a lot more versus the traditional two-dimensional ATC radar? But obviously, you know, ENSPs are always constrained by resources, and cost is an important consideration.
Okay, I think that probably Lola could answer better to this question.
Yeah, I'm gonna answer it. It's
Sorry.
compared to the 2D radar, we can say that the difference can be between 2 to 2.5 million euros. But that's not the question. The question is what is the cost compared to an L-band? You know, because that's where the difference is. We are providing these capabilities of an L-band in a reduced format that it will ease not only the acquisition cost but also the maintenance cost and the infrastructure cost.
Mm-hmm.
So
Yeah.
if you compare with a S-band radar, probably it's a little bit more expensive, but S-band radar has also more limitations. For instance, just about range. So that's why the reason S-band radar are cheaper, let's say, but are used mostly in TMA and approach only, and not for long range. But if you compare the 3D with a traditional L-band 2D radar with parabolic reflector, the costs are very similar, also because of the reduction of the infrastructure if you compare the tower needed by one radar and the other radar. And also with the 3D radar, you can have a lot of advantages in improving the capabilities of the system, in having the same system for short, medium, and long range, reducing cost in maintainability and in operation of the system.
Mm-hmm. Right. Yeah. could you give us an estimate? What's your sense? Well, this will be just an estimate. What is the percentage of ATC radars that are two-dimensional, and what's the percentage that's three-dimensional? I
Okay,
would imagine, you know, most ENSPs will still be using 2D radars, right?
Yeah, for sure. I don't know exactly the figures, but the majority of the radars are 2D radar. You can say 90-10 or 95.5% of the radar. So because this kind of technology was not used in the civil war normally because of its previous cost, because were not really 3D system that could also fulfill the requirements related to civil market about the redundancy and the availability of the system and the reliability. So normally these systems were think and designed in a military war where there was always operator on it, 24 hours operating the system. They had only one channel, and as I said in the presentation, they were not focused in the quality of the data, but in just having the system available in case there is an emergency or an alert and they need to use it. And that's what we have changed, and we want to introduce that, taking out all these military functions that we don't need in air traffic control and civil air traffic control, and including those requirements needed for civil aviation, we can have a radar with a really good price and with the best performance of both worlds to be used in air traffic control, in civil air traffic control.
Yeah, okay, got it. Thanks. One more question. Well, has any of your has any of Indra's customers who are doing civilian ATC work purchased a 3D radar, or is this really leading edge, brand new in the market?
It's quite new in the market, but we already have customers with this radar in operation or in setup in this moment. So I don't know, Lola, if you want to set some of the reference, or if I can tell them some of the reference of the system.
Yeah, for example, in Sweden, we have just now one operating, and I believe, if I'm not wrong, we are about to deliver another 2 more. We are just now delivering a system. It's in the final commissioning stage in UK, in Scotland. Then in Latin America, we have, I don't know if it's around 6 systems.
3 systems in Guatemala. We have there.
Middle East, we have a list in Oman, as far I remember. You know, we have it's in the market from the previous years, but it's been having a good acceptance by our customers.
That's great. Yeah, good to hear. Yeah. It looks like, I'm looking at the clock, it looks like we are out of time. Herman, Lola, any last comments before I close?
No, thank you very much for this opportunity.
Yeah, thank you very much. You know, for those attending the webinar, if they need have some question or anything, they can address us and ask whatever they need.
Right. Yeah, I hope our audience listening in learned something new about radar today. Well, my takeaway is that as the environment gets more challenging, there are technological solutions that we can apply, which is excellent. For instance, you know, drone detection, and as Herman said a few times, there's a possibility for us to get the best of both worlds. So I've enjoyed the session. It just leaves me now to thank Lola and Herman once again. Thank you very much for sharing this very valuable information with us. Thank you. Have a good day, everybody. Bye-bye.